Welcome to the Explainer. Today we're going to tackle a really core concept in probability, how to turn a simple list of chances, a PDF, into something way more powerful, a cumulative distribution function, or CDF. And trust me, we're going to make this super simple.
Okay, let's just dive right in. The whole reason a CDF even exists is to answer this exact question. Your standard probability table is awesome for telling you the chance of one specific thing happening, like, say, rolling exactly a 4 on a die. But what if you want to know the odds of rolling a 4 or less? That's a totally different question, and that's exactly where the CDF shines.
So this slide right here, it lays out the difference perfectly. On one side, you have the PDF, the probability distribution function. Think of it like a laser pointer, focused on one single exact value. But on the other side, you've got the CDF, the cumulative distribution function. This is all about the running total. It's always adding things up, always asking what's the total chance of getting this value or anything smaller.
All right, let's get our hands dirty. The whole process starts with a discrete probability distribution. Now, that sounds super technical, but really, it's just a simple table that lists out all the possible outcomes and the specific chance for each one. That's it.
And here's the exact table we're going to use for this whole explainer. You can imagine this as maybe the number of heads you get from flipping 3 coins. You could get 0 heads, 1, 2, or all 3. And this table tells you the exact probability for each of those. And notice, real quick, if you add up those probabilities, 1/8 plus 3/8 plus 3/8 plus 1/8, you get 8/8, which is 1. Perfect.
Okay, now for the fun part. This is where we actually start to build the CDF. We're going to take that table and just start adding. And that's really the whole trick to it. Don't let all the math notation scare you off. Deep down, a CDF is just a simple running tally. As we move from one outcome to the next, we're just going to add its probability to the total we've built up so far.
So look what we've done here. We've just tacked on a new column to our table, f of x, to keep track of that running total. For the first value, x equals 0, the total so far is just its own probability, 1/8. Easy enough. Then, for x equals 1, we take the previous total, that 1/8, and add the new probability, 3/8, which gives us 4/8. And we just keep doing that all the way down the line.
And here's a fantastic little pro tip from our source material. You see how that very last number in our f of x column is exactly 1? That's how you know you're on the right track. It's like a built-in fact checker. Since all the probabilities have to add up to 1, your final cumulative total must be 1. If it isn't, you know you made a little slip-up somewhere in your addition.
Okay, so we've got our cumulative numbers. Now comes the part that can feel a little tricky at first, turning these numbers into an actual mathematical function. But don't worry, it's all about defining the right ranges, or intervals, and we're just going to break it down into a really clear logical process.
Following these 4 steps is seriously the key to not getting lost. So, step 1. For any value of x before our first outcome, which was 0, the cumulative probability is just 0. Nothing's happened yet. Step 2. For each of our outcomes, we make an interval. And the key is that it includes the start value, but goes right up before the next one. Step 3, we just assign our running total to that whole interval. And finally, step 4, once you hit your very last outcome, the probability is 1, and it just stays 1 forever after that.
And bam, this is what we get. This is our final product. And it's called a piecewise function because, well, it's built in pieces. Just look at that second line. It's saying that for any x between 0 and 1, including 0 but not including 1, the cumulative probability is flat at 1/8. Then, the instant x hits 1, boom, the probability jumps up to 4/8, just like it says on the third line. Each line is one of our running totals.
We've built the function with numbers and symbols, but now let's actually see what it looks like. Graphing this thing really makes the idea of these intervals and jumps click into place.
Now, before we sketch this out, there's one super important rule we gotta cover. You see this here? When our interval includes a number, the less than or equal to sign, we use a solid filled-in dot on the graph. But when the interval goes up to a number, but doesn't actually include it, the less than sign, we use an open, empty circle. This is how we show exactly where each step begins and ends. So, when you put it all together, what does our graph look like? Well, it's not a smooth curve at all. It's a series of flat, horizontal steps, which is why, you guessed it, we call it a step function. It always starts down at 0 on the left, and it always ends up at a height of 1 on the right. And the really cool part? The height of each of those vertical jumps, that's the exact same probability we started with in our very first table.
Right. So we've done all this math, but what's the point? This is way more than just a classroom exercise. The CDF isn't just a different way of writing probabilities down.
It's a genuinely more useful and powerful tool for understanding what's going on.
And here's the payoff. With our CDF, we can answer those bigger questions instantly. What's the probability of getting 2 or fewer heads? We just look at our function, find where x is 2, and bam, the answer is right there, 7/8. No more adding things up. The CDF gives you the complete picture of how probability builds up across the whole range of possibilities.
And there you have it. That's how you go from a simple probability table to a full-blown cumulative distribution function. But here's a final little thought to chew on. Our example used these nice, clean, separate outcomes, 0, 1, 2, and 3. But what if our variable could be any number in a range, like, say, someone's height or the temperature? What do you think would happen to that graph if those steps became infinitely tiny? What would that staircase turn into? Something to think about. Thanks for tuning in.